All right, first study group of phase 2. Congratulations on finishing phase 1. Phase 2 is going to take a little bit of a turn, and I actually wanted to start with like an overview of what phase 2 is all about. If you haven't seen yet, on our study group repo, I've actually uploaded PDFs of these slides. And the next 5 study groups are going to be actually done off of PowerPoint. And I think as you're going through, you'll sort of see why, but it's going to be probability and statistics, of which I think is more important to understand several concepts, which I will highlight during each study group. And coding from scratch is actually not that important. You'll see later on, more so in like sections like 13, 14, 15, they'll have you code out a lot of formulas that are actually already built in. Some pros and cons to coding out formulas. Pros like you get to practice your Python skills, like translating math into code is kind of important. I mean, it's a good way to practice your Python skills. But a con is actually, you'll never need to do that because everything exists in a statistics library, probably SciPy. So do with that what you will. If you feel pretty comfortable with like Python, I would say honestly, you don't have to do a lot of those exercises. But I think for some people, it helps actually understand the concepts through coding. So kind of up to you what you want to do with those kinds of exercises. The goal of phase 2 is actually very different from the first half of material. The goal of phase 2 and the end of phase project is going to be a linear regression project. And I just would like to see like a show of, I don't know, you can either emoji react or like comment in the chat. Like, has anyone, like, how familiar does that sound? Like, have you heard of it? Okay, I see like a couple thumbs up. All right. Anyone like completely, like I say linear regression, that doesn't mean a thing. I guess it's hard to ask like non-yes or no questions. Yeah, I think like through like the one-on-ones, I've found that there are a lot of economics majors in here. And in econ, you do have to do linear regression, but we're actually going to take a very different approach. So yeah. What else? Yeah, so the end goal is to do a linear regression, of which that's kind of in this mod because to properly interpret a linear regression, you need to have some stats background. So through these first few topics, we're actually going to go through like pretty intense statistical testing. But as a data scientist, that's actually very unlikely that you will need to do statistical testing. So just so you know, a lot of the material that we're going to see, we might use in an interpretation sense, but we don't actually conduct that many statistical tests. Same with probability, which is the section we're going through today. It says section instead of topic because the terminology has changed recently, so section equates to topic. But with combinatorics and probability, it is something that statistics is built off of. So it's not super important to like fully understand like all these probability axioms and like memorize them. You really don't have to do that. And if there's anything to remember, you'll sort of see the upcoming warm-up questions that I'll post in the morning will be more probability statistics related. And I will just let you all know that what parts are important. So there is a lot of material to go through in the lessons, but hopefully like knowing this, that like you won't be doing straight up pure statistics, hopefully that lightens the workload a little bit. So yeah, any questions before we get started? Yeah, the math is sometimes a little bit intimidating. I took statistics 3 times before I got comfortable with it. And there are still some parts of it where I'm like, is this what we do? So just know that everybody is a little bit like about stats. So all right, let's get started with this topic's materials, which is combinatorics and probability. And this I label a crash course just because it's like a lot of information for a day's worth of work. And I just want y'all to recognize that. So as an agenda, we're just going to talk very briefly about what probability is and why. And then we're going to talk a little bit about sets. Sets because some interview questions are in sets. Permutations and factorials, which is another set of counting problems. Combinations, another set of counting problems. And I'll talk about like how do you identify which one to use. I think that's a pretty important skill if you want to like really hammer down this stuff. And the last two sections are conditional probability and the law of total probability. 5 and 6, I will actually come back to when we get to topic 17. So I'm not going to go very in-depth into this part right now. I think it's better to focus on the first half of the topic, and then we'll come back to conditional probability later on. Questions so far? All right. So probability, what is it and why? There's a lot of different definitions for probability. I'm sure you have at least dealt with some form of probability in your life. But one definition I found is that the probability of something occurring is its proportion of all possible outcomes. So what's the probability of rolling like a 4 on a 6-sided dice? It's 1 out of 6 because, you know, there's 6 possibilities and you only want the probability of 1 out of 6. More in like math definition terms, the probability of something occurring is its event space. The number of things in its event space over the number of things in its sample space. So rolling a 4, the event space is literally just 4. And in the sample space would be 1, 2, 3, 4, 5, and 6. Those are just, you'll sort of see these terms pop up. And so when you're looking at the probability of like flipping a heads, and when you're flipping a coin, you have heads, tails, 2 outcomes. If you're just looking for flipping a heads, 1 out of 2. Rolling a 5, similar to what I was talking about earlier, things like that. Now, why this is important? It is the basis of statistics, and then also data science interviews. I was talking about this before I started the recording, but some data science interviews do have probability questions. I do think it's not so much about, you know, are you able to solve a problem really fast? I will say that in the cases where I have encountered probability questions, they're more looking out for your critical thinking skills. Like, are you considering all pieces of the puzzle when you're trying to solve this problem? I think it's less so about, you know, getting the right answer, but more about the thought process. So hopefully through these like upcoming topics, it familiarizes you with like, you know, the things to look out for when you get probability questions or statistics questions. All right. Set theory is really just, I think, terminology to begin with. I did mention, I think before the recording started, that I will be holding an extra session sometime next week to just go through the different kinds of questions that you might get. And one of them is on, one area is on set theory. And the terminology that you just have to remember here are union, intersection, and complement. And here you can imagine that I have 3 Venn diagrams. Let's just, I don't know, let me actually like write some examples here. Where is my annotator? All right, so let's just say on the left side, we have event A. And where is my drawing pencil? Here we go. Let's just say this left side one is A, this right side one is B. And let's just say that, all right, these are dice rolls. We'll have A be equal to all even numbers. I'm gonna try writing as nicely as I can. And then B will be any number that's greater or equal to 4. So with these A's and B's, let's fill up this Venn diagram. A being even, or actually let's go number by number. Let's actually start from 6 going down. So 6 is even and is also greater than 4. And so therefore we're gonna put that in the middle because it belongs to both A and B. The number 5 is greater than 4 but isn't even. We're gonna put that in B. The number 4, similar case to 6, we're gonna put that here. 3 actually belongs, and this one sometimes trips people up, 3 actually belongs outside here. 2 goes in here, and 1 also belongs outside here. That's my attempt at a comma, so let's ignore that. But anyways, usually a Venn diagram, the proper way to draw a Venn diagram, you have this box around it. And the box actually denotes your entire sample space. And then any bubbles within the Venn diagram are your different event spaces. So is the setting up of a Venn diagram clear? Anything to clarify? All right. So here we have union, intersection, and complement. It kind of is already here based on like, the shading of these bubbles. I'll just quickly talk about it. The union is this one. And it's basically what is in both A and B. So if we did A union B, which another way of having it is like this, you might see this like U symbol. A union B is everything that exists in A and in B. Sorry, in A or in B. I always get confused with that myself. But it's basically a union, so you want things that are in A but and or in B. I think what is easier if I were to shade it in. So let me get a different color. A union B is this entire thing. So A union B are the numbers 2, 4, 5, and 6. Kind of opposite to that, we have intersection, which is more of this one. And intersection are only the ones that are both in A and B. And so in this case, it would just be the numbers 4 and 6. Finally, and just to have this here, the symbol for intersection is like an upside down U. And then finally, you have complement. Complement is an interesting one because complement you can sort of think of as the opposite of. So in this case, let's actually take a look at what is the complement of A. So here we have A, and A is, we're gonna keep A as this left circle. So this entire circle is A. Now the complement of A, and two different ways to write complement. You might see A with an apostrophe, that also means complement, or you might see A with a little superscript C, that also means complement. And complement basically means anything that isn't A. Something that does trip people up is anything that isn't A actually includes the square. So if I were to shade what the complement is, I'm going to use this pink color. Complement of A is actually this entire area. And so what elements belong in complement A? You have 1 and 3 that were actually outside any of the bubbles, but you also have 5, which was in this like crescent part. So any questions on, let me just draw this arrow here for.
Isn't that the absolute complement, or is it just the complement? Like,
I know that in the lessons they talk about 2 different kinds of complement. I honestly have only seen, I have not encountered looking at the differences between the 2 complements.
Okay.
So typically you only see just complement, and then that would just be everything that isn't that. So I wouldn't worry about that part too much.
Like the whole sample space.
That's right.
Like not including whatever's in A.
That's right.
Okay.
Yeah.
Yeah, this one is absolute complement, and the other one that Sarah is mentioning is relative complement, which only includes the green part in this one, except the sample.
Gotcha.
Yeah.
Okay.
That was my hunch as well. I'm hesitant to talk about like absolute versus relative complement, because when we get to conditional probability, that actually complicates it a little bit. But thank you so much for that, Ali. Any other questions on this part so far? Awesome. Okay, let me clear all of these drawings. Let's talk about the next thing. All right, so we've sort of talked about this already, sample space and event space. Sample space is all possible outcomes, and the event space is one, a subset of sample space, and it's based on the probability we want to calculate. So I think that's pretty self-explanatory. Anyone need more explanation on this? Cool. So something that may or may not come up is thinking of probability in terms of the law of relative frequency. So how probability arises And I'll actually talk about this in a future topic when we talk about frequentist statistics. But the probability of an event is the ratio of positive trials to the total number of trials as we do an infinite number of trials. So imagine where that is derived is, let's say we want to find the probability of rolling a 5 on a dice, right? How you sort of derive that probability, yes, it is sample space out of event space, but you can also think of it as, I'm going to roll a dice an infinite number of times, and the proportion of the number of times that it comes up as a 5 is going to be 1 out of 6. So that's another way of sort of thinking about probability. I'm going to like repeat this experiment of throwing a dice over and over again till the end of time. And the number of times that it turns out to be 5 will be 1/6 out of all the times. And that's just another framework of thinking of probability, just to be aware of. Questions about that? Cool. All right. Now, these are some probability axioms, which I think at some level are kind of like duh, but are just good to know that these are actual rules that exist in the world of probability. So first of all, positivity. The probability of an event is always going to be between 0 and 1, between and including 0 and 1. You cannot have any probability less than 0. You can't have any probability more than 1. That's just because probability is a fraction. It is a proportion of something. Next, a certain event. A certain event is basically something that is certain to happen, where the event is equivalent to your sample space. So let's say you, for some reason, have this extremely weighted die that only can roll 4s. The probability of rolling a 4, because it is equivalent to your sample space is only 4 because it can only roll 4s. The probability of rolling a 4 in that case is 1 because it's certain to happen. And finally, additivity. This one takes a little bit of thinking, but I think I should write this down in a different way. The probability of the union of 2 exclusive events is equal to the sum of probabilities of each event. Let me actually draw some diagrams. All right. So here we have, I'm going to draw a mini Venn diagram here. Here we have our sample space. I'm also going to draw 2 events, and we'll sort of see what this is illustrating. So here, I'm going to have event A. Oh, that's not nice. I'm going to redo that. Here we have event A, and then here we have event B. Doesn't matter what the values are, but just to show that this is one event, and this is another event. So what this additivity axiom is saying, the probability of the union of A and B, so the probability of A union B is equal to probability of A plus B. So in this case, probability of A plus the probability of B. But this only can happen if these two do not intersect. Gotcha? So this only holds, this equation here only holds if A and B don't intersect at all. That also leads to the addition law of probability, because if they do intersect, and let me try and draw another one as quickly as I can. If we have another situation where they do overlap, and so let's see, we have one here and one here, and left is A, right is B. If they do overlap, you cannot really say that the union of these probabilities is the sum of their parts. One way to think about it that really helps me is, let's see, here, is the probability of A is this part here, this left bubble. If we're adding the probability of B, pick a different color. If we're adding the probability of B, that's this entire part, also including this middle part. What's happening here is we're double counting the middle, right? We're double counting the middle in this situation, which is why with the addition law of probability, if they intersect, we actually have to minus 1 time the probability of this intersection point. Any clarifications? Nice. This actually can be expanded to more bubbles. If anyone's interested, it's actually called the inclusion-exclusion principle, which for one case is just the addition law of probability. But basically, this equation actually does also hold for this case up here, because this part, when they're separate, would just be 0. This is something that's good to know. Questions before I move on from this? All right. Next, we're moving on to factorials. Factorials, permutations, combinations are all different methods of counting. They're not really fractions. You do incorporate them in calculating probability, but these are actually just different counting methods. I'll actually go into this when I talk about some of the questions next week, but there are sometimes ways that you want to like do it fully by hand than using formula. But all right, first we're going to talk about factorials. Factorials are exciting because they have exclamation points, and they're denoted by exclamation points. And when you see a number followed by an exclamation point, it actually is just the product of all the integers leading up to that number. So, for example, if I had 5 factorial, if I had 5 exclamation point, 5 exclamation point evaluates to 1 times 2 times 3 times 4 times 5, which I think is 120, if anyone wants to fact check that. Similar, it can go to as big, as many numbers as you want. I think if you do like factorial 10, it's about like 3 million something. And yeah, because they are, multiplying bigger and bigger numbers, the numbers grow very, very quickly. So that's what a factorial is. One probability use case, if you are looking for the number of ways to arrange n objects, you would use factorial. So for example, let's say we just want to arrange A, B, C, the 3 letters A, B, and C. There are 3 factorial ways to arrange 3 objects. So as you can see here, 3 factorial is 6, because 1 times 2 times 3 is 6. And there just happens to be 6 ways to arrange A, B, and C. I have written by hand this up to 5 factorial times. So I can confirm that it works, but feel free to find out for yourself. But yeah, it does scale. So if you're looking for the number of ways to arrange like 8 different things, it evaluates to 8 factorial different ways. So if you're ever asked, like, all right, for example, like how many ways, I think one of the examples that's used in a lesson is like, if I'm a band that has like 8 songs, how many different ways can I have an 8-song set? Like how many different ways can I arrange the 8 songs? It would be 8 factorial ways. So that's this use case. Questions before I move on to the next one? Cool. All right. So one step further from factorials, we have permutations. So permutations is usually talked about with combinations, counting methods that help us find the size of our probability spaces. So with permutation, it is the number of ways to arrange k out of n items. So kind of different from factorials. Factorials, we were just arranging n items. Here, we just want to see how many ways I can arrange a subset of those items. And usually they tell you how many items they want to be arranging. So the formula for this, I'll talk about the formula a bit later. But an example is, we're talking about this band example. They have 8 songs, but they want to play a set of 3 songs for, let's say they have this concert where they can only play 3 songs. How many different 3-song sets are there? And in this case, it's important to remember that a different order of the same songs will count as a different set. That's a really important fact to remember. A different order of the same songs will count as a different set. And to evaluate this, the formula is n factorial divided by n minus k factorial. Here you can see that it's 8 factorial divided by 5 factorial, which is 336. Another way to think about this that may or may not be helpful for some of you is I have actually let me get my pencil out again. I've actually seen this way of thinking about this problem, and maybe that might help. So let's use the same example of you have 8 songs and you want to find out how many sets of 3 songs how many different 3 song sets there are. I sort of saw this example as saying, all right, I have 3 empty slots of songs here. And I just want to find out how many different ways I can fill in these empty slots. And by the way, this way of thinking might not make sense for everybody. I just want to preface that. It just seems to help for some people. But anyways, I have 3 empty slots here. One way to go about this problem is think about, all right, this first slot can be, there are 8 possibilities of songs to go in this first slot. So I haven't set anything yet, but now I have 8 possibilities of songs to play as my first song. So after this, after I've had my first slot filled with any one of 8 songs, after this first slot is filled, in my second slot, I now have 7 options of songs after, choosing a first song. And then that leads to like 7 different options for songs to choose in your second slot. And then after that, in a similar fashion, after you've chosen your first and second song, you're left with 6 different choices. And with this, you just end up multiplying these numbers, which gives you the same result as using this permutation formula. For some people, and also actually interestingly for some probability questions, this way of thinking might help, but it's just a different way of framing a permutation problem. But yeah, questions about that? Cool. Let me clear this real quick. Next, combinations. This is the last one we're going to talk about in terms of counting. It's just factorials, permutations, combinations. So combinations, quite similar to permutations, where you're looking at the number of ways to choose k out of n items. However, the order of your items doesn't matter. So if I was like using this example, a different order of the same songs will count as the same set. So here there's a slightly different example. If I have a collection of like 8 seashells and I want to randomly pick 3 to give away, how many combinations of 3 shells are there? So you can see, like, if I happen to pick, let's say in like different trials of picking, I end up picking the same 3 shells but in different orders. Those count as like the same set of shells. And so for that, because there are repetitions, the number actually turns out to be smaller. That's one thing that also that helps me think about when to use permutation and combination. The number you expect will be smaller. Because here the formula will be n factorial divided by the product of n minus k factorial times k factorial. So here we're dividing by 5 factorial times 3 factorial, where previously we don't have that 3 factorial here, so the number is bigger. So before we had 336, but here we only have 56. With this formula, you're using factorials. I also wanted to mention there is another way that this is notated that I wanted to mention. You might see in some labs, you might see this kind of notation where you have like these tall brackets, kind of looks like fractions, but doesn't have a line in between them. You might see this. So in this case, it would be 8 and 3. This is the exact same thing as 8 factorial divided by 5 factorial times 3 factorial. Yeah, just know that if you see this kind of notation, that's the same thing as this. This shorthand only exists for combinations, not for permutations. I'm not sure why. But if you see that, just know that that equates to that. So to like sort of summarize this counting portion, factorial is just a number of ways to arrange a set of things. Permutations is a subset of things where each different order matters. And combination is you're also doing, groups of a subset of things, but the order doesn't matter. Questions on this part? All right. Yeah, I recognize that it is a lot of information. So if a lot of this is like, all right, I sort of get the concepts, I think that's good enough for now. All right, next, conditional probability. We will come back to this in section topic 17. But conditional probability is the probability of something occurring given that something has already happened, which is a very important concept for Bayesian statistics. We'll get into the whole realm of Bayesian statistics, I believe next week, or if not the week after. But sometimes you're given conditions that have already happened. So the formula to remember, and you may or may not choose to memorize this, is the probability of A given B is equal to the probability of A and B, so A intersect B, over probability of B. I'm not going to go super into it, but a way of thinking about it is B has already happened, right? And so our realm of possibility is now only within B. And let me actually think of an example. An example, let me see if I have an example here first. Okay, no, I guess I don't. But all right, so let's say, what's the probability that you bring an umbrella given that you know it's going to rain? So if you know it's going to rain versus if you know it's not going to rain, you have sort of different probabilities of whether you're going to bring an umbrella or not, right? If you don't think it's going to rain, you're probably not going to bring an umbrella. If you know it's going to rain, you're going to bring one. And so you sort of think of it as like, all right, let's say the event B is it's going to rain. Your probability of A, which is the event that you bring an umbrella, is going to be affected and segmented by that. I'm not going to get super into it because I'm going to have a whole nother thing talking about conditional probability. But any questions about that? I'm not sure. I don't think that was a good explanation, to be honest, but I am going to talk about it more later. Is
it just the intersection of A and B then?
Yep, that's right. It is this A and B does refer to the intersection of A and B.
And then divided by the probability of B?
Mm-hmm. Yeah. So one way to think about it, which may or may not make sense right now, is your sample space is now made smaller. Because you sort of, you have that condition, you have that given thing. So your sample space is now smaller. And in this case, your sample space is now B.
Okay.
So one way of thinking about what's the probability of A given B is what proportion of B is also A.
So then A and B, in this case, the intersection would be like your event space, and then the probability of B would be the whole like sample space?
Yeah, that's right.
So then it'd be like your event space divided by your sample space.
Mm-hmm.
Okay.
Yeah. I will come back to conditional probability like next week, so I wouldn't worry too much about this. This next slide is going to look pretty intense. I know I like flipped over it for a little bit, but this is the law of total probability. This one is especially important in my opinion because almost all the probability questions I've seen in interviews include this law of total probability. It's really just a formula, but that formula stems from if you know the proportion of each of these. Okay, so here, let me explain this diagram. Here we have our entire sample space. And first, let's just look at the rectangles. The blue rectangles, you happen to have 4 blue rectangles, A, 1, 2, 3, and 4. So the law of total probability is, for some reason, let's say that you know what proportion of this A1 is B, and you know what proportion of A2 is also B, and what proportion of A3 is also B, you can find out the total probability of B. If this doesn't make sense right now, I will have actual concrete questions that use this that I will go through. But just to know that the law of total probability is something that, as you're preparing for interviews, I do recommend that you try and remember. I don't know, you don't have to make a note of it, but when we go through the questions next week, I will go through examples that use the law of total probability. One example question that you might see is, let's say you know the accuracy of a drug test. So for example, like now we're looking at vaccines, and it's actually very apt right now that we're talking about this. If you know the overall accuracy of a coronavirus test, so for example, like if you have, let's say there's an overall accuracy of about 99%. I actually know it's not 99. It's probably not 99% honestly, but 99% accuracy is basically saying, all right, if you have COVID, 99% of the time they'll tell you that you have COVID, but 1% of the time they'll tell you you don't. Opposite is true, where like if you don't actually have COVID, 99% of the time they'll tell you you don't have COVID, but 1% of the time you'll get like a false positive. So here you have like a 1% false positive and a 1% false negative rate. So now let's say you know that out of the entire population, maybe about 20% of everybody has COVID. So now that you have this information, if you were to go out and take a COVID test and it comes out positive, what is the probability that you actually do have COVID? I think some people would think, all right, yeah, if you have the test result of 99%, it means, there's 99% chance that you actually do have COVID. But we'll see that using the law of total probability, that isn't actually the case. I think with a 1% infection rate, so this is just like numbers that I know from a specific problem. If 1% of the population has COVID and there's a 99% accuracy rate on the drug, if you were to test positive, there's only 50% chance that you actually have it. And we'll talk about how I derived this. I think this is actually the exact problem in one of the lessons, I think, but I'll go through it. But it's very interesting to think about it that way. And I won't talk about it today, but we'll talk about it next week. I think this is my last slide, actually. Yeah. Does anyone have any questions about this stuff so far? Cool, awesome. Let's see, things I wanted to mention. If you don't have your new working group set up yet, someone just take initiative and do that. And if you don't have it set up by the end of the week and you don't want to do that, just let me know. Also, project review is going well so far. I think I've figured out the grading system. So basically you'll receive a 1 or a 0 on your assignment, depending if you pass or not pass. So if you see like a 1, don't think that it's like a 1 out of 10, just to let you know. 1 is pass, 0 is not pass. And I think on a separate thing, you'll receive like a full like scoring sheet. But yeah, I think the main thing I wanted to say is that if you see like a 1, it's a good thing. All right, what else? Yeah, any final questions on this topic?
Yeah, I think earlier you had mentioned something about like if there was a union between two things that they to like find that probability they couldn't intersect. Could we maybe just go back to that part? I think I just wanted to clarify that.
Yeah, absolutely. I think it's this one, right?
Yes.
Let me actually like draw it with my whiteboard. I think that might make sense. I actually think there's a problem in one of the lessons that I'm gonna just like make up some numbers with, but same kind of problem. So the question on one of the lessons is, I believe, you have, I'm gonna make up some numbers and I'm gonna draw this out. So let's say you have A and B. So here we have this Venn diagram, A and B. Actually, let me unshare my screen so you can see this. All right, we can see this more clearly now. All right, so I have this like Venn diagram of A and B. And let's actually use the fact that, all right, A is the probability that someone has a Visa card and B is someone having an Amex card. So let's say that you know the probability of, or at least the proportion of people that has a Visa. So A, the probability of A is 50%, and the probability of B is, let's use 40%. So here you have 50 and 40. And I believe one of the other stats, I guess it doesn't really matter which number it is. But here, let's just say that the probability, the proportion of people that have no credit card at all is, let's do 20%. So this is 0.2. 0.2 is out here. Does this setup make sense? That we have like 50% of the population having a Visa, 40% having an Amex, you know that there are some people that have both, but we don't know how many people. And then also we have 0.2 of the population that don't have any credit cards. Make sense?
That makes sense so far.
Cool. All right. So I think in the problem, they actually might be giving you like different parts of the puzzle, but this all still fits together. So here we have, let me actually just write this in a different way. And let me know if I need to like, there we go. So here I can first say, for here I can first say that the probability of A union B complement is 0.2. Basically that's saying that everything that isn't an A union B, so neither A nor B, so A union B complement is 0.2. That's why this outside part is 0.2. You can sort of guess that there's an overlap because it doesn't make sense if A is 50, B is 40, it kind of adds to greater than 1, so you know that there's got to be some overlap. So now to figure out what the overlap is, actually let me see if we can actually do that. To figure out what that overlap is, we can use this formula. I don't have space to write it, but let me just edit this so that we have space. All right, so we use the formula of A union B equals to A plus B minus A intersect B. So this is that law of additivity. Is it additivity? Yeah, law of additivity formula that we had, right? Where the probability of A union B is equal to A plus B minus this middle intersect. And we have to minus this intersect because there's some, I'll try and like weave that into my explanation at some point. But basically, we have A union B here. And since we know that 0.2 is A union B complement, A union B is 0.8, right? A and B are 0.5 and 0.4 respectively. So we have 0.5 and 0.4 respectively. And now we can find that this intersect in the middle is 0.1. That's right. Yeah. So this middle part is 0.1. This middle part is 0.1. This outside part is 0.2. And we can sort of like fill in the rest of the blanks. This entire A circle is 0.5, but this crescent part of the circle would be 0.4 because this middle part is 0.1. So let me get rid of this 0.5 just for now. And then similarly, because this entire B bubble is 0.4, this like crescent part is 0.3. So we can get rid of that. This is a little clearer. So what we're saying is before, we had, just A 0.5, just B is 0.4. If we were just to simply add them together, we actually wouldn't get the right number because 0.5, 0.4 is 0.9. And since we know that this outside part is 0.2, it doesn't all add up to 1. It adds up to more than 1. Therefore, we have to deal with this overlap part in the middle. That sometimes you're just given different numbers of this whole entire puzzle that you just have to figure it out. What part was not clear? I feel like I just rambled on about a lot of numbers. But hopefully this makes things a little clearer. The main thing is that because there are some people that have both visas and Amexes, you have to deal with this overlap part. And if we were to, just take 0.5 plus 0.4, we would actually be double counting the 0.1 part, right? Because 0.5, 0.4 comes out to 0.9. This part is actually 0.8. And so we actually double counted this middle part of 0.1, which is why this formula down here, we're minusing away the intersect.
I think that makes sense. Thank you.
Yeah, we'll talk about this. Yeah, I actually have one of these kinds of questions in that list of questions that I'm going to go through. But yeah, anything else? I will say probability is a hard one to pick up, especially in a day. I took an entire semester just looking at probability, not even statistics. And yeah, it's hard. So yeah, any other questions?
Is the law of total probability the game show type of scenario where, like, let's make a deal where you have 3 doors. You can choose one door, and then they give you the opportunity to choose it after you find out that the one wasn't it, or is that something else?
Kind of. So the law of probability is actually derived from Bayes' theorem, which I'm not sure is mentioned in this topic or only later. But Bayes' theorem is conditional probability. And that problem, which actually specifically is called the Monty Hall problem, where like basically to just reset it up for everybody, you have 3 doors. Behind one of the doors, you have a car. Behind the other 2 doors, for some reason, it's a goat. You have goats behind the other 2 doors. And the idea is, as a game show contestant, you choose one door. After you've chosen one door, the show host, I guess, will reveal what's behind another door. And then you have to decide, do I keep the door that I chose or should I switch my door? And then actually you can actually derive through like conditional probability. I think if you were to switch your door, I think if you were to switch your door, you actually have double the chance of winning your car.
Yeah.
And we'll actually talk about that specific problem in section 17. But yeah, that is derived off of conditional probability. And if anyone's interested in that, there is actually a lesson simulating that problem and like all of those probabilities as well. I will say not important to know how to code out like a simulation of a probability problem, but just like a cool thing to see that if you were like to run this experiment, like I think they have you do it like 10,000 times, it will come out that like 1/3 of the time you will win if you choose to stay, and 2/3 of the time you'll win if you switch your door. Yeah, that's an interesting one to think about. A lot of YouTube videos about it as well. Okay, so if there are no other questions about this part, going once.
It's not a question so much, but I just had the idea that I don't have like an educational statistical background, but for the past 5-6 years, I've been dealing in a casino. So I was thinking if any other students would like a practical hands-on lesson for how the game of craps once, I could show you like dice probabilities, and I give like a little short lesson on how the house makes money. So if anybody would like to for me to set up a Zoom, I could take like 30 minutes and walk you guys through that sort of thing. And I know I learn better when I have like hands-on reason why the numbers make sense as opposed to like formulas. So if you just want to like put something in interest in the in our Slack, I would totally be up for doing something like that.
Oh, that's so awesome. Thanks,
That's
Tim.
great. I'd go to that.
Or you can learn to gamble. Step 1 is done.
Yeah, that's
Just
awesome.
stay away.
I will, I'll actually help. I can set up the Zoom for you. You can use one of my Zoom links for that. But yeah, that's a great thing. Why don't you like set up like, I can actually set up a poll with like, maybe some people can put suggestions for times to set that up. Yeah, thanks Tim for offering to do that.
Yeah, I could tell you times I'm available and we can just put that in Slack and just let me know.
Awesome. Yeah, I actually will say that I only learned poker from a bunch of my students. And like my last few months like on campus were just losing some money. I'm personally not good at gambling, but anyways, I digress. Any other questions about probability? Because I did want to talk about what to expect. Cool. Let's see, Tim, I'll just get the info from you and then I can just like make like a Slack poll and then you can all set that up. So the next few topics, so topics 12 through 16 are gonna be pretty heavy on the stats theory. As I mentioned before, on Canvas, there are a lot of lessons, a lot of which, you know, they have you hard coding a lot of these statistical things. And again, you can do that if you want to, but I don't think it's particularly helpful for most people. So just know that. What I am going to send out after this is a YouTube playlist by this guy named Josh Starmer. I don't know if anyone's heard of StatQuest, but this guy is incredible. He used to be a professor, I think, and he just makes these really fun like Microsoft Paint looking videos explaining a lot of statistical concepts really, really well. Like I think better than I could ever explain them. So I'm going to send out that playlist. each of his videos does correspond to a part of our curriculum. So as you're going through curriculum, if you are finding that, you know, maybe like written out in words, some things are just not clicking or a little bit too dense, just look up the corresponding video. So yeah, I'm gonna send that out. Really, really good playlist, highly recommend. I mean, even I guess if you're like, I don't know, I used to do this when I'm having lunch, I'll just like watch a couple of his videos and learn. I think just having things shown in a different perspective, and he actually does it from a very data science perspective too. So less like stats theory, just like theoretical stuff. So I'm gonna send that out. So just know that that's an additional resource. I do have a couple book recommendations that I do have like links for free PDFs that I will share as well, if you prefer, you know, reading more textbook like resources. But again, you would have to do a little bit of the work of like matching up which sections to read. But yeah, just to let you know, not everybody likes the way that it is set up on Canvas is not, it doesn't work for everybody. So if you're finding that things are just not sticking, it's not on you, because there are many different ways that you can pick up stats knowledge. But yeah, any questions about that? Cool. Well, we're pretty much right at time. I will see you guys all tomorrow, and just let me know if there is anything that comes up.
Thank you.
Thank you. Bye, everybody.
Thank you.